I'm Brianna Tullier, and I'm the Group 1 leader for the gas turbine jet engine. So we'll outline of what we'll be going over today. So there's some background theory objectives that we'll be learning. So the apparatus, the experimental procedure that we'll be doing, the post-lab, and conclusions and predictions. So this is the system that we'll be using during the experiment, the turbogen gas turbine electrical generation system. So some background about it. So the system converts rotational mechanical energy into electricity. So this type of energy is typically used by the electrical power generation industry. So there are two different types of plants. There's a base load and a peaker plant. So the base load plant will supply the majority of the electricity needed day-to-day basis. And then on high demand days, such as a hot day that uses a lot of air conditioning, peaker plants are started up to generate the enough electricity to make up for the base load shortfall. So some theory behind this. So the goal is to maximize efficiency, and a way to do that, so higher operating temperatures could create higher thermal efficiencies, as well as a heat recovery system. So how you recover the energy given off by the turbine's exhaust. So for simple turbines, efficiencies can range from 20 to 35% to 60 to 80%, depending on how the heat is captured and released back into the system, which means the heat recovery system. So some objectives about the experiments is to gain an understanding of the turbogen gas turbine electrical generation system, to plot experimental data and use the first law of thermodynamics for analysis of the system in the post-lab, to evaluate the system performance and determine the optimal operating settings to calculate power-specific load consumption. So this is the apparatus we'll be using. So the turbogen gas turbine electrical generation system contains the SR30 turbojet system, a TG2000 turbo electric generator, and then the operational controls, or the operational panel showed here, which has the master switch for the start, stop, the power lever, the load lever, and a digital and analog display which will show the temperature, pressure, RPM, or speed, and the voltage. So then next to the system will be a computer standing on its own, which will have the standard turbogen software, which will be used to monitor and record conditions and log all of the experimental data. So how the engine works: the air will enter the intake of the engine and then is compressed by the centrifugal compressor. Air will then mix with the fuel and combust, which creates the thrust to drive the power turbine. So the experimental procedure will be outlined in the expanded normal procedures of the turbogen operator's manual. There's a lot of stuff to put in here, so it's best to just go back and follow that step by step. So for pre-start, you will do a visual inspection, including like the clear shield that is in front of the engine, as well as follow all safety precautions. So for startup, operation, and shutdown, you will use the one-touch system that will monitor the parameters. You will use the throttle for the engine to reach full speed and then capture operational values. So for the data acquisition on the computer, it will log all the experimental data. So for the post-lab, whenever everything is done, you are supposed to graphically plot the turbogen data to prepare for system analysis and performance calculations. For the plots, you will do a pressure, temperature, fuel flow, RPM, or the speed, voltage, current, and power, all versus time. And then you will select an analysis point at time where the engine RPM peaks and record the conditions at the selected time. The point will be the basis for the system performance and analysis calculations. So continuing the post-lab, for the system analysis, you will use the first law of energy conservation equation for a steady state, steady flow with data from the plots that you make. And then you will find the specific enthalpy at different cycle points using the air tables and calculate work and energy at selected cycle points. For the engine performance analysis, you will evaluate the system performance at the compressor inlet and the nozzle exit. So for the electrical generation performance analysis, you calculate the power-specific fuel consumption and process of generating electricity, which is the fuel consumption of energy divided by the electric power produced by the generator. So the safety precautions to follow during the procedure is to wear hearing protection, use safety glasses in case anything explodes, know where the fire extinguisher is, and then locate the master switch to power off in case anything happens, as well as do not exceed the suggested measurement limitations. For the conclusions, so the peaker plant is not typically used in industrial power supply, only to account for shortfalls that the base load cannot account for. And then the apparatus consists of a turbojet engine, electrical generator controls, and the turbogen software. And there are extensive operation procedures to be carefully followed during the experiment.